Okay, so let's unpack this. We are constantly hearing about this arms race in AI right now. It's always bigger models, more data, and these massive GPU clusters that use, honestly, enough electricity to power a small country.
Right. Yeah, it's a lot.
It really feels like every single week there's a new model that's just twice the size of the last one. But there is a massive kind of elephant in the room problem with this obsession with size.
It's the cost. And I don't just mean the millions of dollars required to train these things, though. That is obviously a factor. I mean the time and the sheer computational energy. We're basically hitting a wall. It's
Yeah.
becoming completely unsustainable.
Exactly. It's like we're trying to build faster cars by just strapping more and more engines to the roof. Eventually the thing is just too heavy to even move.
Yeah, exactly.
But today we are looking at a paper that might just have, well, they might have found a way to cheat the physics of this whole system. We are doing a deep dive into the paper, Switch Transformers Scaling to Trillion Parameter Models with Simple and Efficient Sparsity.
And this is a really significant piece of work coming out of Google. The authors, William Fetus-Beardzoff and Noam Shazir, aren't just trying to make a bigger model here. They're essentially trying to break what we call the power law.
The power law. Okay, that sounds a little ominous.
It's more just mathematical destiny, I guess. In deep learning, usually if you want a smarter model, you have to add more parameters.
Right.
You think of parameters as the synapses in a brain. But the rule has always been if you add more parameters, you proportionally increase the computational cost. The actual amount of math required to process every single word or token.
So it's a one-to-one penalty.
Exactly, one-to-one penalty.
So if I make the brain twice as big, it takes twice as long to think a thought.
Precisely. Up until this paper, at least. These researchers managed to scale a model to over 1 trillion parameters, which is a massive milestone on its own.
Yeah, 1 trillion is wild.
It really is. But here's the hook. They did it while keeping the computational cost per input roughly constant.
Wait, hold on. So the brain got massive, like trillion parameter, massive, but it thinks just as fast as the smaller models.
Even faster, actually. They achieved up to a 7x increase in pre-training speed compared to the standard models we use today.
I mean, that sounds like magic. Or, honestly, accounting fraud. How do you get something for nothing like that?
It's not magic, it's sparsity. And to understand why this is such a big deal, we really have to look at why we haven't done this before. We have to talk about the hardware lottery.
The hardware lottery? I thought we were talking about neural networks today.
We are. But here's the thing. For the last decade, all of our hardware, like GPUs and TPUs, has been optimized for dense matrix multiplication.
Okay.
They love big, solid blocks of numbers. They are incredibly efficient at crunching dense data. Because the hardware was good at that, researchers naturally built dense models to fit the hardware. It's a feedback loop.
Okay, so let's define dense in this context, because most of the famous models we talk about on this deep dive, like the standard transformers or GPT-3 or T5, they are dense models. What does that actually mean under the hood?
In a dense model, every time you feed it an input, say a word or a sentence, the model uses every single one of its parameters to process that input. It activates the entire network.
So if I ask the model, what is 2 plus 2, it's firing the exact same billions of neurons as if I asked it to explain the geopolitical nuances of 19th century Europe.
Exactly. It's incredibly inefficient when you think about it. Imagine a general practitioner doctor. This doctor tries to solve every single medical problem that walks through the door personally.
Right.
Whether you have a cold, a broken leg, or you need complex heart surgery, this one doctor tries to use their entire medical education to treat you.
That doctor's going to burn out pretty fast. And honestly, I don't really want a GP doing my heart surgery just because they read about it once in med school.
Right. And that's a dense model. It works, but it's wasteful. Now contrast that with the solution this paper proposes, which is a sparse model. Specifically something called a mixture of experts, or MOE.
Okay, I like this. So keep going with the hospital analogy.
So in a sparse model, you don't have one overworked GP. You have a massive hospital filled with specialists, your experts.
Right.
You have a cardiologist, a podiatrist, a neurologist, a pediatrician. When a patient comes in and that's your data token, they don't see everyone in the building. They are routed to the specific expert that knows how to handle their specific issue.
So the hospital building itself is huge. It has way more staff or parameters than the single doctor's office.
Outrageous numbers of parameters, actually. That's how the original papers termed it. We're talking about scaling from billions up to trillions.
But for any specific patient, You're only using a tiny fraction of the staff. I mean, the podiatrist isn't scrubbing in for the heart surgery.
Exactly. You activate a tiny subset of the weights for each incoming example.
Mm.
So you get the capacity of a massive model, a full trillion parameters worth of knowledge, but the computational cost of the much smaller one.
Yeah.
Because you're ignoring 99% of the parameters for any given action.
That makes intuitive sense. It really does. But mixture of experts isn't a brand new concept, right? I feel like I've heard this term floating around research circles for a few years now. Why hasn't this taken over the world yet?
You're right. The idea dates back to the 90s, and Shazir, one of the authors of this paper, actually tried to revive it for modern transformers around 2017. But there was a big problem.
Which was?
It was complicated. The communication costs between computer chips were really high, and honestly, the models were just a nightmare to train. They were highly unstable.
Unstable how? Like they would just spout gibberish at the end.
Or just crash completely. The math would literally break. And they were extremely complex. The old way of doing MOE involved routing a token to multiple experts at once.
Like getting a second opinion.
Sort of, yeah. You'd send a token to maybe the top 2 or top 3 experts, compare the results, and then mathematically combine them.
Why send it to multiple, though? Just to be safe?
Partly for safety, but mainly because of the math involved in learning, specifically calculating gradients. The underlying assumption in the field was that you needed at least 2 experts to compare against each other to get a smooth signal for the model to actually learn anything. If you just pick one, it's what we call a discrete choice. And discrete choices are notoriously hard to differentiate through in calculus.
So the industry standard was basically pick a few experts, average them out, and hope the math holds together.
Basically, yes. And this is exactly where the switch paper drops the bomb. They looked at that core assumption and just said, nah, we don't need to do that.
They just ignored it.
They simplified the routing algorithm down to the absolute limit. They decided to route to one expert, just k equals 1.
Just one. I mean, that seems risky. What if the router picks the wrong one? There's no backup. There's no second opinion.
That was the exact fear everyone had. But it turns out if you design the router correctly, it works beautifully. By routing to only one expert, you instantly have the batch size needed at each expert. You drastically reduce the communication traffic between devices, and surprisingly, you completely preserve the model quality.
So simplicity wins out.
Simplicity scales. That's the key takeaway here. Previous MOE models were like trying to coordinate a full committee meeting for every single minor decision.
Right.
The switch transformer just appoints a CEO for that specific decision and moves on immediately.
Okay, I'm stuck on this router concept, though. You've got a trillion parameters. How does the model know instantly which expert to pick? Is there like a master controller sitting on top?
It's not a master controller in the sense of a separate brain. The router is actually a very simple neural network gate sitting inside the layers of the model itself.
Okay.
It looks at the incoming token, say the word apple, and it runs a really quick calculation against all the available experts. It assigns a probability to each one.
So it looks at apple and thinks expert A is 60% likely to know about fruit. Expert B is 5% likely. Expert C is 0% likely.
Exactly. It uses a mathematical function called a softmax to turn those raw scores into percentages or probabilities. And since it's a switch model with k equals 1, it just grabs the single expert with the highest probability. The winner takes it all.
But this raises a massive logistical nightmare, doesn't it? What happens if everyone wants to see the same expert?
Ah, yes, the heart specialist problem.
Yeah, I mean, if the model decides that one specific expert is the smart one for really common words like the or, and then everyone gets sent there, the other experts are just sitting around playing cards in the break room, and that one expert is completely overwhelmed.
Exactly. In computing terms, that one expert becomes a severe bottleneck. The whole system slows down to the speed of that one overloaded expert, and you completely lose all your parallel processing benefits. So to fix this, the authors introduced the concept of expert capacity.
Which is like a waiting room limit for the doctor.
Ideally, yes. Expert capacity is a strict fixed limit on how many tokens an expert is allowed to handle in one single batch.
How do they decide that number?
They calculate it by taking the total number of tokens in the batch, dividing it by the number of experts, and then adding a little buffer. They call it a capacity factor, usually set to about 1.0 to 1.25.
Okay, so they have a little wiggle room built in. But here's the part that concerns me. What happens if the expert is actually full? If the heart specialist is at absolute capacity and another heart patient walks through the door?
The token is dropped.
Well, wait, hold on. Dropped. You mean deleted. We spend millions of dollars collecting this data, scrubbing it, processing it, and the model just decides, nah, I'm full, and throws it in the trash.
I know it sounds heretical, doesn't it? In traditional software engineering, dropping data like that is a critical failure.
Hmm.
But here they view it very differently.
How so? Because that still sounds like a bug to me.
Think of it like a busy highway during rush hour. If an exit ramp, let's say the exit to downtown, is completely gridlocked and backing up onto the main highway, what do? If you stop the entire interstate to wait for that one exit to clear industry, you destroy the flow of traffic for everyone. The whole system halts.
Okay, so you force the cars to stay on the highway and just keep moving to the next exit.
Exactly. If they pause the entire computation to wait for that one expert to free up the speed advantage,
Yeah.
which is the whole reason we're building a sparse model, it just evaporates.
Right.
So the token skips that specific expert layer entirely. It doesn't perform the calculation inside the expert. Instead, it moves via a residual connection directly to the next layer in the network.
So it effectively skips a grade. It doesn't learn from that specific expert, but it's not totally deleted from existence. It still flows through the rest of the network layers.
Correct. And crucially, this dropping usually only happens during training, not necessarily during inference, if you size things right. But, the authors were worried about this too. They didn't just assume it was fine. They actually tried a really clever experiment called No Token Left Behind.
I love the names these researchers come up with.
I know, right? The idea is pretty simple. If the first expert is full, try the second best. If that one's full, try the third. Just keep rerouting the token until it finds a home.
Which sounds completely logical. Why waste the data if you don't have to?
Logical, yes, but incredibly slow. It actually failed.
Really?
Or rather, it didn't help performance enough to justify the massive extra complexity and the communication overhead between the chips. It turns out simply dropping the token and letting that residual connection handle it works perfectly fine, provided you don't drop too many tokens.
Well, so how do they ensure they don't drop too many? How do they stop all the tokens from rushing the same expert in the first place?
They use something called a load balancing loss. It's an auxiliary loss function.
Basically a penalty during training.
Precisely. It punishes the model mathematically if the router tries to send too many tokens to just one expert, or if the router becomes too confident in picking just one expert all the time.
So it effectively incentivizes the router, to be fair. It says, hey, spread the work around or I'm going to give you a bad grade.
Exactly. It forces the system to utilize the entire hospital staff, not just crowd the ER.
Okay, so we have a simplified router, we have experts, and we have a way to balance the load. But earlier you mentioned these MOE things are a nightmare to train, that they really like to crash. What actually changed here? How did they keep this 1.6 trillion parameter beast from just falling apart mid-training?
This is where we get into the real engineering nuggets of the paper.
Yeah.
They had to make some very specific low-level adjustments to the math itself. And one of the biggest issues they faced was precision.
You mean like how many decimal places the computers are using?
Yes, exactly. Usually to make training really fast on modern hardware, like TPUs, you use a number format called bfloat16. It uses fewer bits than the standard float32, so it's significantly faster, and uses way less memory.
But it's less precise.
Right.
It's like measuring a room with a ruler that only has inch marks versus one that has exact millimeters.
That's a perfect way to look at it. And for most of the massive neural network, that inch mark precision is completely fine. It works. But the router uses exponential functions to calculate those routing probabilities we talked about.
And exponential functions are incredibly sensitive.
Extremely. If your inputs are even slightly off because of that low precision, the exponential function can just explode. You get massive unmanageable numbers, or you get NaN.
Not a number.
Right. The model literally forgets how to do math, and the whole training run crashes.
It's like trying to land a rocket on the moon, but you decided to round pi down to just 3.
And you miss the moon by 100,000 miles.
Yeah.
Exactly. So they were stuck in this catch-22. If they use bfloat16, the model crashes. They use float32, they run out of memory, and the training takes forever.
So what's the actual fix?
Selective precision. They realized they could cast only the specific router calculations to float32. So the router does its highly sensitive math in high precision to decide exactly where the token goes the surgical strike, and then the data is instantly cast back down to bfloat16 for all the heavy lifting in the expert layers.
That is so smart. It's using the laser measure for the critical cut and then just using the big hammer for the nail.
It really is. It stabilized the training entirely without losing any of the speed benefits. But that wasn't the only trick. They also changed how they initialized the weights of the network.
This is the 0.1x thing I saw in the notes, right?
Yes. In standard transformers, you initialize the weights, the starting values of the artificial brain, with a certain mathematical scale. The authors found that by reducing that standard initialization scale by a factor of 10, it drastically improved stability.
It's almost a classic chaos theory thing. Making sure the starting conditions are incredibly small and controlled prevents the entire system from spiraling out of control 50 steps later.
Exactly. And there was one more major trick regarding overfitting. Because if you have a trillion parameters, isn't there a huge risk
hmm
the model just memorizes everything?
Right, like a student who memorizes the entire textbook word for word but then fails the final exam because they don't actually know how to apply the knowledge.
Yeah, it's a huge risk,
Hmm.
especially when you take this massive trillion parameter model and try to fine-tune it later on a really small specific task. To fight this, they introduced something called expert dropout.
Now, normal dropout is when you randomly turn off certain neurons during training just to force the network to be robust and not rely on any one pathway right.
Correct. And usually you use a dropout rate of maybe zero point 0.1, so 10%. But for the switch transformer, they cranked that dial way up inside the experts. They used a dropout rate of 0.4,
Wait, 40%?
40%, specifically within the expert layers.
Wow, so nearly half of the expert's brain is just turned off at any given moment during training.
Yes, it seems drastic, but it forces those experts to be incredibly robust and completely prevents them from just rote memorizing specific training examples.
Okay, so they built a better router, they balanced the load, and they fixed the mathematical stability issues. The big question is, does it actually work? What are the final numbers?
The numbers are frankly ridiculous. Let's look at the speed stats first. They compared a switch-based model to a standard T5-based model.
Okay.
To reach the exact same quality level, the same level of smartness, the switch model was 7 times faster.
7 times is huge. That's the difference between a researcher training a model for a whole week versus just treating it for a day. That changes the iteration cycle completely.
It does. And even when they compared it to T5 Large, which uses 3.5 times more computation per token, the switch base was still 2.5 times faster. It's just fundamentally a more efficient architecture.
And then there's the monster, right? The Switch C.
The switch C, 1.6 trillion parameters, 2,048 individual experts. To give you some context here, the T5XXL was the previous heavyweight champion in this specific Google lineage. The Switch C trained 4 times faster than the T5XXL, despite being vastly, vastly larger in parameter count.
But speed is one thing. Does it actually know anything? Or is it just a really fast idiot?
No, it definitely knows things. They tested extensively on downstream tasks. It absolutely crushed it on knowledge-heavy tasks, things like trivia QA, natural questions, and web questions.
Which honestly makes sense, right? If you have a massive hospital of experts, you can store a ton of really specific facts. You have one specialist for obscure 18th century poetry and another specialist entirely for quantum mechanics.
Exactly. The raw capacity for memorization and fact retrieval is enormous. It also performed exceptionally well in multilingual settings, which is huge.
Oh, really?
Yeah, they tested it on 101 different languages, and it beat the multilingual T5 baseline across the board.
Huh.
In fact, for 91% of those languages, they saw a 4x or greater speed up.
That is wild. But here is where I have to play devil's advocate for a second.
Go for it.
You and I are sitting here casually talking about trillion parameter models. I don't have a supercomputer in my basement. I highly suspect most of our listeners don't either. If this model is so impossibly big that it needs a Google-sized warehouse of TPUs to even run, does it actually matter for the real world? Or is this just a massive flex for Google?
That is a really important point to make, because if you can't actually deploy it, it's just an expensive science experiment.
Right.
But the authors anticipate this exact critique. They included a very crucial section in the paper on distillation.
Distillation. I usually associate that with making whiskey, but I'm guessing in this context we're boiling down the model.
In a way, yes. Think of the massive Switch C model, not as the final product you ship to a phone, but as the teacher. You have this wise, ancient master who knows literally everything.
But you can't bring the master to every single job site.
Exactly. So you train an apprentice. You use the massive sparse teacher model to train a tiny, dense student model, like a standard T5 base. The student basically just tries to mimic the teacher's answers over and over.
And how much quality do you actually lose doing that? Because usually the apprentice isn't nearly as good as the master.
You do lose some, of course,
Right.
but the results here were really fascinating. They show that you can compress these massive sparse models by up to 99%.
99% compression, so you shrink it all the way back down to a normal size.
You shrink it back to the size of a standard model that you could actually run on reasonable everyday hardware. And critically, that tiny student model preserved about 30% of the quality gains from the massive teacher.
Okay, so you get a very significant chunk of that supercomputer performance, but packed into a dense package that fits in a regular server rack.
Exactly. It means that these massive, sparse models can act as upstream knowledge reservoirs. We use the trillion-parameter monsters in the data center to discover all the complex patterns, and then we distill that wisdom down into something highly practical for the rest of us.
That makes this feel a lot more practical, honestly. It bridges the gap between research at the absolute edge of possibility and actual applications we might see on our phones one day.
It does. It completely solves the deployment issue.
So looking at the big picture here, what does this all mean for the future of AI architecture? Because it feels like we are swinging a giant pendulum. We went from small, dense models to massive, dense models, and now we're swinging over to massive, sparse models.
I think we are seeing a necessary correction. For a long time, the hardware lottery forced the entire industry into density. But this paper proves that with the right algorithm, this really simple switch k equals 1 mechanism, you can overcome that hardware bias. You can finally unlock the efficiency of sparsity even on our current hardware.
It fundamentally proves that increasing parameters doesn't have to mean increasing computational cost.
Yes, that is the core breakthrough. But in these papers, there was one final aha moment in the research that was a bit puzzling. A paradox, really. And I think it's the perfect provocative thought to leave you with today.
I love a good paradox. Lay it on me.
The authors noted a really strange anomaly when testing. The massive 1.6 trillion parameter model Switch C had noticeably better pre-training scores. It had lower perplexity, which basically means he was less confused by the language it was reading.
Yeah.
It just knew more.
Okay, so the bigger brain worked better. That tracks.
Yeah. In general, yes. But when they took that model and fine-tuned it on reasoning tasks, specifically the Super GLUE benchmark, which asks the model to actually use logic and solve problems, it sometimes performed worse than a smaller version of the model, the Switch XXL.
Wait, the bigger brain was actually worse at reasoning. How is that even possible?
Here's the catch. The smaller model Switch XXL had fewer parameters total, but it was structurally set up to use more FLOPS, more actual computation per token.
Ah.
The trillion parameter model had way more memory because of all the parameters, but it thought less per token because of how extremely sparse it was.
That is fascinating. So the trillion parameter model is kind of like an encyclopedia. It contains all the discrete facts in the universe, but it can't necessarily connect them together well. Whereas the smaller model is like a detective. It knows fewer facts overall, but it works much harder to actually solve the case.
That's exactly the implication. It suggests there is a very poorly understood relationship right now between fine-tuning quality FLOPS and parameter count. It raises a massive question for the field. If a model knows everything but doesn't do enough computation to connect the dots, is it truly intelligent?
Wow. It really comes down to the fundamental difference between knowledge and reasoning. We've apparently solved how to stuff near infinite knowledge into the box using sparsity, but maybe we haven't quite solved how to make the box think deeply about that knowledge yet.
And finding that balance between knowing and thinking might just be the next great hurdle in AI.
Well, on that note, we will leave you to ponder. Are you building an encyclopedia or a detective? Thanks for diving deep with us on the Switch Transformer.
It's been a pleasure.
See you next time.